Okay, can I ask a question? Because I saw in the email there are another link for this afternoon session. So are we using a different link for every session?
Yeah, to fix the streaming problem, so we have to do that like separately.
Okay, so there will be like a different link for tomorrow's session, right?
Yeah.
Okay, yep. Perfect. I think people are getting in. Okay, I'll also post tonight's session in here. So for tonight's tutorial, we will be using another link again. So I have posted that link for tonight's session also in the chat room. It's also in the email that's just sent. Just a reminder, like each session is different link from now on. Okay, so okay, so Guanqi, can you send the link for the auditors? Yep, there's in the new YouTube link for the auditors.
Yeah, okay, I will send them right now.
Yep, great, thank you. Okay, for the participating students, does anyone want to start like sharing their best neural network results from last night? You're up. A lot of questions. So I'll start with whoever just near me. So Boshen, hi, are you there? Hello. Yep, since you're right below me, so it starts from you. Okay. All right, you're out. So you can just share your screen on your best PDF. Wait, 1 minute. Let me get my song away. This.
Hi, I hope you can hear me okay.
Yes, yes, perfectly.
Great. I will share my result from yesterday. The way I investigate in this particular study, because I wasn't sure what each activation function would do, so I decided to categorize, well, try to kind of more organizing the activation function with different combination of different activated functions and different dropout. So to kind of briefly summarize, I use Relu and Sigmoid as a two primary activation functions, and then I tried the variety combination of them. I do want to point out one mistake I made was when I record the score, I record the validation loss instead the actual score. But I will quickly jump to the final, the best results that I had, which is the two Relu activated functions combined together. Although I did find the Relu plus Sigmoid activation function also give me a pretty good result as well. And
sorry. There's
yeah,
nothing on your screen. Are you have you started showing things?
Oh.
Like currently we're seeing your Google Calendar.
I'm very sorry. I must share the wrong screen. Very sorry about that.
We're in your WhatsApp chat now.
let me drag this over. I'm not sure why this is happening. Sorry about that. So I guess I will just jump to the best result here. So the best result I got is the Relu and plus Relu activation functions. As I pointed out earlier, I also tried the Relu plus Sigmoid and Sigmoid and Sigmoid. All of the three combinations, I think the Relu plus Relu and Relu one performed the best. The second one is the second best one is Relu plus Sigmoid. When I did the dropout earlier, either with dropout with Relu or dropout with Sigmoid, I think the training still learns, but it has a little bit zigzagging performance toward to the end. So I think that's we will address it this afternoon, how to improve that later.
Just a question, because I saw in your output shape, like in your previous model, most of them are like 512, and then in this like final one, which didn't perform really good, it's like you start with 2 layers of 16, and then like 512, and then like in the final one.
Yes, so the final one, because I did 2 activation functions together, I think that's where the 512 was. Yeah.
So I think the 512 is in the model structure. It can be changed in the dense. So if you would move to the last one, yeah, we're just trying to debug like when something works like significantly better. Maybe like another, like the last one, like the one I remember is like the loss is like 0.03 or something, like a very bad one.
Oh yeah, this
that
one.
one. So I'm wondering if anyone has noticed here. So like you have 2 layers of 16. So remember how many dimensions we have. So we start with 80 dimensions. And then you have like 2 layers of 16. It's not necessarily this cost, because people does sort of start to lower their dimensions a lot, especially image processing. But because this case, we still need to expand, go back to 80. So I think it could, and here is like this layer is like 512. So just some intuition ways to see why some models works better than other. So because you start with 2 very small layers, it's possible that a lot of information is lost when you put like 80 numbers to 16 numbers and try to expand it back to 18 numbers. So normally I would try, so maybe a 512 may be too much, but I would consider for earlier iterations, try like 64 neurons, or at least like 33 neurons, and see if the performance is to see if this would be the problem of your model. So if this one would be like the bottleneck of your model.
Okay, that makes sense.
Yeah. And another thing about Sigmoid and Relu, can you go back to one like with only Relu and one with only Sigmoid? So this is
Yes.
only Sigmoid, it's like 0.02. And what about the Relu one? Yep.
Sorry, yeah.
So you see like the Relu is a lot better, at least in this case, than Sigmoid. So this is like a one, let me just share my screen.
Yeah, I mean.
Sorry. So if you remember, like Sigmoid looks like, so this is the one. 0, 1. If I think this is sigmoid, unless I'm confusing. So sigmoid looks like this. Wait, I think it's 0. Yeah. Let me check. I'm confusing sigmoid with another function. Yep, this is a sigmoid. Here is this one. So if you look at the form of the sigmoid itself, so it will quickly become 0 or it will quickly become 1. So this is x. So hypothetically, if you're having x, let's say like 10, it will only be almost 1. And if you're having like x like -5, it will be almost 0. So for sigmoid, it will quickly categorize whatever in x to 0 and 1. So look at this activation function. So it means whatever you're giving the input is, it will quickly push it to 2 edges, like either 1 there and or there or either 0 for the output of this activation program. So this one is really good for classification. Remember, like the 0 and 1 issue, dog or not a dog, cat or not a cat question. So the sigmoid is very good for this kind of classification question, but it will be slightly less effective for the regression, because regression basically you want like them to still have value here, but for sigmoid it will be only sensible to the value difference in this middle region. So that's why the sigmoid classification. Sorry. So that's why sigmoid are like almost a mass use for the classification purpose, but it will be slightly less effective for this kind of regression issues. And on the contrary, if we're looking at the Relu program, Relu activation. So for Relu activation, it sort of looks like this. So it's like no matter how big you're expanding your inputs are, it will still give you like a reasonable amount of domain for the outputs. So unlike the sigmoid, it will just restrict the number to 0 and 1. So the value will go up a lot. Okay, so that's 2 tips for your neural network. So anyone want to show your own neural network and we can sort of debug a little bit? Okay, so Amir, you're next to me, sorry. Is it because your name started with an A, so you're like always on top?
Oh, I'm sorry, I can't fluent speaking English, but I share my screen
Yep.
to show my source score.
Yep. Yep.
The show.
Yes.
I'm sorry, I just saved the best score, but I use deep deep layer to I use as Relu 4-layer Relu and it let me to show Anaconda Jupiter. I should run the Jupiter. I'm sorry.
Don't worry. I think while you're trying to open the Jupyter, I can just add something about this one. So I think this one is quite interesting because if we have noticed the value, so this one, I remember proportion like your best is like also 0.0111 or 0.012, right? Oh, so it's okay.
Yeah,
so,
that's right.
So if you have noticed for Amir's his neural net, so he has a lot more neuron than you. You have like 16 to 156. He basically has let me clear this up. Yeah, so he basically have like 206, like 512, 512, 1,000, like 204, 1,024. So basically for his neural network, he has far more neurons than you. But if you have noticed that the performance did not increase like significantly, so just have get some intuitive idea. So we have a set amount of data. I think that in this case, I forgot it's like 20,000 or something. And can you scroll down a little bit, Emil? Can you just scroll down? Yeah, like here, just down a little bit. I want to see the like end of all those text. Yeah, about. Let me stop. Yeah, here. Down a little bit, just here. Yeah. So you see the total parameters. So we only have, so our each sample is only 80 parameters for each sample, and we only have like 20, like less than 20,000 samples. So imagine if you're having like this huge network, but you only have limited data. It's likely that some of the neurons will not be activated in the process, or just some of them just didn't receive enough information. So it's very common in when you're training a neural network, like as you increase in layers and increase in the neurons, like the general outcome does increase, but they don't increase indefinitely. They will increase to a level that are like more or less limited by the like size of your data sets. So like the larger the neural networks, for example, like for him, like so for Amir's neural network, it's not that deep, but it has like a lot, many neurons. But because with the restriction on our data set size, at a certain point, it will reach a threshold that the like, let's say the performance doesn't increase because we don't have that many data to active all and calibrate all the neurons. It is like a common thing phenomenon in neural work trainings. Like when you start to increase the size of your neural network, at the point like the performance just sort of stop increasing. And I'm not sure if Amir has noticed like this is a quite big one, and probably it takes quite some time to train one epoch. So this one will take far longer than yours. So it's a lot of them are the balance of performance and like how many neurons you want and like how long of time you got, because currently we're having very simple data, so each sample is only 80 numbers. But imagine if you're working with a 60 by 64 by 3 image, even a very small image, it's going to take forever for one iteration. So it's like a balance between things. So, Amir, do you have other models to show, or just this one?
Yes,
Yeah.
I test Sigmoid 10 and I changed the optimizer. I check the website cares and check every each parameter to change and for 4 hours more maybe more I changed the parameter to best score. I
So can, yep. So is this another model?
Yes.
Awesome. Yep, I think this is the one you're
Yes.
showing. Yeah. In your PDF.
PDF. No, PDF. Just save the best.
Yep.
The best score.
So, yep. So you can see it's a lot bigger than yours, than a lot bigger than Boshan's. But I mean, because our test is very easy, like the data structure and the relationship is very easy. So all of the models were able to capture like the essence of the relationship. It's just how to fine tune it to increase the accuracy.
Yes.
So do you have like a special feeling, Amir, like if certain thing works better than the others? Like the bigger network works better, or like more layers works better? Is there anything that's just instantly make your system works better? Do you have this kind of feelings because you changed a lot of parameters? So I think this is a good example of a very big neural net. So anyone want to offer your own? Because we probably won't have time to go through all 20.
Sorry, Dan.
Yep.
May I ask a question regarding to Amir's loss? Because I kind of had
Yes.
the same issue in one of my trials.
Yes.
If we look at the loss, like the loss of the test is much lower than the loss of the training. I mean, the loss in validation is much lower. Is this normal? Because actually, I mean, generally, the model should be more accurate.
Let me
this
see. It's like a loss lower. Like, is this in everyone's case? If that's the case, it's probably with the labeling. I labeled them wrong, but I'm just checking because I didn't notice. No, okay. I think
it wasn't in all of my trials. In some of them, it was like this, but not all of them.
Okay, I think there are a few issues. So, I think it's maybe problem if we have shuffled them. I'm not exactly sure about this case, but normally there are a few issues that can cause this problem. The one main issue is that we didn't shuffle our data sets. So for example, imagine just saying, or it's just start to shuffle in a way that puts like similar things together. So remember we have did data augmentation. So it's basically like this. If this is like a one strip, it was cut down into like different parts. So there are probably like 10 piece of our training samples coming out of like one strip. So imagine if we put, let's say, 9 of them. I think our split is like 70, 30 split. So imagine if we put like randomly like 7 of them in our testing set, and we put in the training set, and we put like 20, like 20% or 2 or 3 in the training set, in the test, so validation set. So it's not training. So this one is actually validation set. So it's one with validation. Yeah. So it's not training testing. So this is like training validation. So in this case, because for example, for each strip, it has like probably this part already seen in the test, in the training, and part of it has already seen in another testing samples. So because of the data augmentation, so even though those two are considered as like new samples, but maybe like 99% of this sample is already seen in the testing process. So this is a case that we make the validation set and the testing set very close together. And if they're like very close together, for example, like I think in this moment, it's like a very small percentage. It can happen that the validation set is actually have like lower error than the testing set. It's because like the data distribution is not uniform. So remember, in this case, we are having the testing set like a wide range of things, but maybe in the validation set, like the majority of it just come from like 4 pieces that we can predict very accurately. So data distribution is like one crucial issues that we need to consider. And it's also depending on where we're collecting the data from. For example, if we start to split, for example, if it's a facial recognition program and the most of the image we downloaded from internet. And then we start to use our classmates image for validation, or we added some we added a data set of our classmates image into the data set, but we forgot to shuffle it. So if that's the case, it will result in very, very poor accuracy, because from the internet, if we download image from the internet, it would probably be like mostly, I don't know, white people's picture, but while my classmates may be like Asian in their teens. So this one could, because of the unbalanced distribution of the data set, it can cause like huge error between validation, testing, or validation, or training and testing. So yeah. So it's a lot of them are depending on the distribution, or that we're having let's say a model that are training on like a variety of people of all genders, but because there are more, let's say, white people's image in it, it maybe perform better on the white people's image. But if in the validation side, it's all the image from white people, so it's likely that it performs better on the validation set because it's all white people, which it works better. While in the training set, it's like a portion white people, a portion Asian people, a portion like African American people. So that's in the end, like the validation works better because the distribution is different. That's why there are a lot of questions about like moral issues of the neural nets. So because of this imbalanced distribution of the data sets, it can cause a different set of variables. So I would test like shuffle the data a little bit more and see if this problem still persists.
Yeah, thank you.
Yeah. So are there anyone who like to share your like scores? So has anyone achieved better than this score? Like, so currently the best we have is like 0.01.
Can I share mine?
Yes, for sure.
PDF. Yes, I hope you can all see this. This is what I've done. I put several layers and I put gradually increasing for the input and gradually decreasing for the output. So I guess this is the lowest point that I get. Therefore, I try to punch more the epoch. So this is for I try for the 500 epochs.
So you can see like the zigzagging problem at the end of the epoch. So it start to decrease at the certain moment, but at the very end, because your step is too big, like our learning rate, because currently it's like a uniform learning rate, because the uniform learning rate is too big. So it has a difficult to converge to near the end. It start to have this kind of zigzagging effect and the bouncing around. So this is like definitely the kind of moment when we need to consider to give it like a learning rate decay or manually just save the model and retrain it with the lower learning rate. Do you have this model saved? I
Yes,
think
I do.
yep. Later I'll show you like a method. You can load this model again into your computer and retrain it with a lower, smaller learning rate. So and it's likely that your model can still like become better.
Okay.
Yep. So our currently the best score is 0.07. Anyone want to give another shot? Has anyone achieved better than this?
May I show my screen as well?
Yep.
So that's the best score I've got. And the action, like the function I used was Sigmoid, actually, for the first 4 layers. And the last one was tangent.
Mm.
And then I trained it for 200 epochs. And then I think it kind of started to plateau, the loss.
So I think you found the biggest bug in the code I have distributed. So if we look at like all the previous people's the layers, you would say like, because yours better is because you have changed this number. So in the like in the code I distributed, like the mean bug is in the first layer. So the first layer is 16. So we start with limiting like 80 inputs. We just limit them to like 16 neurons in the first layer. And only the information like these 16 values gets like pushed forward to the later layers. So I think like the first layer would be a threshold, a bottleneck in this structure. So even though you would get like still get a certain level of accuracy and improve if you have like very dedicated like later hidden layers, but there are like there would be more potential if you guys would consider have like more neurons on the first layer, so we don't just start with the bottleneck in here. So I think this is a part of the reason that your model works very, very well.
Wow.
And of course, I think there are also like a balance of the layer depths and the number of neurons here.
Yeah.
So currently our best is 0.0006. Anyone got better numbers? Yeah, it's very interesting just to compare neural nets and see what works and what's bad, what didn't work. So anyone got better numbers? Okay, so the best we can get with a typical neural nets is about 0.06. We'll just keep that record for now. And let's see if we can achieve better with other systems. So, one moment. Is anyone talking? No. Oh, okay, one moment. Okay, so maybe let's say which one we'll start. So I'll give another like very basic introduction about the recurrent neural network, and we will move on to the code and see how this one works. So the concept of the recurrent neural network is very simple. Remember when we're having the dense neural net it's almost like everything connects with everything in the previous layer. I think I have briefly mentioned it in the morning, so it's like really dense, a lot of connections, and etc. So the recurrent neural network actually emerged during our task of speech recognition and or like language translation and etc. So if we are looking at the language, for example, I eat my dinner today in Brisbane. So let's say if we're inputting like each word in a neuron, and imagine if we're having a dense network. So basically this one is like taking equally amount of image from all the previous one. And this one is like taking all the same amount of information for all the previous one. Imagine like this neuron would be a bit difficult to find the connection, because as a natural language, the maybe like dinner may be related to eat. Maybe this two has some correlations, and this one in the activity state and time, like those one may have some hidden connections. So if we're having like this kind of like very typical neural network, it is difficult to increase their productivity and accuracy just by adding more layers, because this one doesn't have connections between the neurons. So that's why there are so the big difference between the recurrent neural network and the dense neural network. So the recurrent neural network is not only taking in the information from the previous layers, but they're also taking in information from the neighbors. One moment. Wait. How to? Okay, so maybe I'll just annotate here. I normally put a recurrent layer on the first layer for a number of reasons, but you don't have to. But the problem is just with data structure. So normally we have, so for example, this is the input layer, x1, x2 to xn. And this is a neuron on the upper layer. And of course, this one will fit to the neuron above it. So, but this neuron doesn't read from all the other neurons. But what it does, it will process the information from here and pass it on to the next one, and then pass on to the next one, and pass on to the next one. Of course, there are a lot of parameters you can tweak in this process. There's a parameter, I forgot what's it called. So basically, like for example, it's coming here. So there's a something like x1. And here is some like z1. So it's after this neurons processing, it's turned the x1 into a z1 and coming here. And this one takes in the z1 and x1 and pops out like a z2. And this one like pops out a z3. So you see, like, because this one keeps staggering together, so the z3 is actually a sorry. Later. One moment. Okay, so you can see like the these three will taking like will be a result of not only X3, but also impacted by Z2, which Z2 will be impacted by Z1. So in this case, it's not only it's taking in the information from the lower layers, it's also taking consecutive accumulated information from like the previous neurons to this one. Let's say the N. And that because this system is very interesting because it creates a few potentials. So I'm just going to introduce how it's classically used and how we can from like typical structure to think about if it to be adaptive for our model or not. So let's then. So there are a few ways to use it. So one way is to let this one taking the information from the both side and just pop out another. Pop out like A1, A2, A3, like AN. So those become like new neurons and you can connect it to other dense layers. So those are, so basically you can, sorry, this one. Yep. So you can combine different structures. The idea is very easy. You process this one and get the output from here, and then you connect with other dense layers and go like forward and forward. So this is the one method to use it. And this is like what we're going to use it in this workshop. But this one has far more potential than just in this case. Oh, just some idea, just some thoughts. Do you think this one will have better performance than our typical neural network in our scenario, in this workshop, in our current data set? It's a tricky question, but if you just use some of intuition, the answer is normally is yes. The reason is that, so remember we're working with like bending. So do you think the height and the angle of this feature point will have somewhat of a relationship to its neighboring point? Normally, yes. Like very intuitively, you would say yes, because like the height may have some relationship with its neighbors. It's like gradient, which means its slope will also have some relationship with the gradient. So naturally, if you think of this this system, so naturally you sort of anticipate this one would perform better on our data set, and we will try to see if this is the case. But there are several few things in this model to play with. Maybe not in our case, but if you're having more complicated tasks, especially speech recognition. So this one is very good for speech recognition. They also have something called forget gate. So remember here, like in this value, would accumulate the effects from all the previous days. And imagine if this is a speech, like a sentence or a paragraph of 100 words that you are inputting in here. Probably like your last sentence, the word in your last sentence is not relevant to the word like 20 characters before or 20 words before. So they have like a very interesting feature like forget gates. So it will randomly forget some inputs. Well, it's like dropouts, but in different manners. So they do have something called forget gate. That we're not going to use, but it's very important in natural language processing. So it will start to the impact of the earlier like some of the earlier, let's say, neurons will be forget at the certain point. They also have another method So for example, the one we're using is long and short-term memory. So why is it called long and short-term memory, even though we're just only going to use the basic features? Remember, like for each of the step, it will go through this process. For example, in this case, so the Z1 is 100% based on the input of X1. And after this one, the Z2 may be 50% based on the input of X1 and 50% based on the input of X2. And at the Z3, you will notice in this kind of proportion, it will be 25% based on X1, 25% based on X2, and 50% based on X3. And on the next in the next neuron, like the X1 will decrease to, the impact will be decreased to like 12.5%. So this is like simplified version, but in fact, the math is a lot more complicated. But it has like the same, follow the same principle. So you would see like the impact of X1 start to decrease after certain, like through this neural net. But remember, we're still talking about speech recognition. So I would say in English, sometimes we say, I eat like pizza, which like it's the national food of Italian, like have like this very long insertion, like at 12 today. Or so maybe like this part is actually relate to this part, while like all those insertions are just something that breaks the pattern. So they also have another like forget gate or remember gate that's what they call the long-term memory. They have like long-term memory, short-term memory. So normally those is like short-term memory because these neurons will be more impacted by its like close neighbors, and this is their long-term memory. So the forget gate not only allow you to forget, but it will allow you to suddenly remember some things from like long way back. So this is why it's called long and short-term memory. So it's if you're having something that maybe like having a lot of this kind of insertions, this may happen. So another ideas of how to using it. For example, if you're trying to predict, let's say, the tourist in each day over a number of years, we would say because each year we have like Christmas and the New Year, Christmas and all the normal days, and we have like Christmas and all the other days in the Christmas. So consider using this one because you may, for example, what happened in November would probably give you some reference to what happened around Christmas, but what happens around previous Christmas is also very important to predict what will happen in this Christmas. So this is like the very interesting feature of the sequence model, and the special one we're going to use the like long short-term memory. But because the nature of our material, we will not use the forget gate, but it's just be mindful that it is derived from natural language processing. It's very good to work with material that has a sequence, that has like speech pattern, or it has like a time sequence, because of those properties. Another thing is just a very minor thing that maybe I'll just talk about it when we start the code, but it's just a minor thing about data structures. So each of the neural net structures, they have their own requirement. They do have their own very explicit data requirement. So remember, for our neural net, our data structure is like something like this. So those are our amount of our samples. And the 80. So those are our input dimensions. So basically for each of sample, we just put all the numbers in a same basket. But for it, this is mainly because like everyone just taking information from everyone. So it makes sense that we treat each neurons, like each inputs, and put them all into a same basket because all the neurons will be relating to each one. But remember when we're talking about the sequence model, it's very different. So this one only going here, and this one only going here. This one only going here, and there is no this kind of connection, but the connection there are like there are horizontal connection between the layers. So in this case, the STM it stands for long short term memory. Long short-term memory. So it's very straightforward. So in this one, the input structure should be 1, 1, 2, 4. So this number doesn't matter depending on how many data set, how many samples you have. 80 and 1. So it needs to have like the last one, the last dimension need to be 1. So they could like only 1. So instead of putting 80 data in one basket, we need to last layer, we need to have 80 baskets, each has 1 data in it. So this is just a very specific data structure requirement for this model. So when we're looking at the code today, you will have a lot of like reformatting the data to let it be compatible with the other part of the program. It's mainly because of this one. Like we cannot put 80 pieces of data in one basket. We need to put them in 80 different baskets. Yep. And as some expansion, let's say some expanding information about this one. So this one is not only very good for image recognition, it's also very good for encoding and excoding between different medias. So considering if we're having a task, so for other tasks, so it's not going to be used by our like the very simple data sets we're having today, but probably if you're doing research, you would probably be able to use this one. So for example, we want to generate a neural net that looks at a location, for example, a country view. Or how about this one? We start with a historical text that is said like the bucolic culture of British countryside and the picturesque scenery. So basically a poet or a historical text that describe a garden. British picturesque garden. And you're trying to generate a neural network that would make a painting according to this description. I don't know. Does this one sound like something architects gonna use? Like you're taking some notes from client and it sort of generates a design for you. Well, so if that's the case, then this kind of LSTM or recurrent neural network is definitely your selection because it has this kind of special function. So remember, we start with all the input. Let's say the input is our text. And it will coming and putting here. And instead of let it output and connect with dense other neural network layers above, so we don't do this. So we don't do this one here. So instead, what we could do is that we let it put here, come out here. So this one looks like one neuron, but it's not one number. So this one could be like it's a dimension is your given. So this one could be like a 524 dimension feature vectors describing all the information you have gathered from this text. So those will, I mean, because this number is something you could assign. You want it to be 524. It could be like 20 dimension. It could be like 64 dimension. But remember, this one is in the end, it's encoded into something. And those are the feature vectors that will be embedded with all the information from this text you're given. So consider this is a encoder. Like all the information about this poem is put in this code. And of course, this will be a high dimensional vector that no human can interpret. But if we have to give it some reference, consider it's something to say if there's a tree in there, if there are a lot of green, if it's romantic, if it's like, I don't know if it's in the winter, if it's in summer. So if we have to give some reference, just consider those are the vectors describe what's happening here. Of course, it will be abstract vectors. No one can understand, but they're basically the features from here. Then there's another like RNN that instead of taking in from each of the bottom, it takes in from here and start to decode. And then maybe there are like other connections here to another deep net. So this one is decoder. So it will take in all the features that it reads from our text and decode it into the features for an image. And then this one will use for this kind of like generative neural nets to generate a drawing that is like based on the poem and the description of the poem. It will generate a drawing that best match the atmosphere and the description in the poem. So this kind of model, the sequence model, is very good for translation between image and the text. So this is like one of the more advanced applications. Oops. Okay, so that's the part the background information that we're going to talk about for the LSTM. So are there any questions before we start to move on to the code and see what happens? So any ideas about this kind of model structure, what you could potentially use it for? Yep, I assume everyone is quickly thinking. So maybe we'll have a quick 5-minute coffee break and we'll be back at 3:15 for some exercise with the coding. Is that okay? Yep. See you guys in 7 minutes. Hello. Is everyone back? Perfect. Yeah. At least some are back. Great. If you don't want to show your face, you can just raise your hand so we know like people are back from the coffee break. Okay, perfect. One moment. YouTube. Okay, I need to let myself in. So maybe we'll quickly just follow the logic of LSTM and quickly tweak the code and have the LSTM running before we go back to the image processing from yesterday. Yeah, I know it's some leftover content. I'm trying to find some time to cover it. So could you please open the model, like the model file, and you would probably prefer to save it as a backup. Just save a backup just in case you have break it and there's no way of returning. Just try to save it first. Yep, a moment. See if this one works. Yep, stop. So a few things to change in order to add our sequence model. So remember we're having, just go all the way down to the model, to this one. Like when you're changing out the layers. So first of all, you can add, there are a few new layers. We're seeing the first one is a batch normalization. So it's another layer that we haven't used before. But if you have following the morning lecture, so this is just to normalize your crazy parameters, just to make the distribution more even. And some people, if you're building like a very deep neural net, some people like to batch normalize every layer. Like I personally would batch normalize like every few layers if you're having like many layers, because it's a non-linear system, and it's possible that after a few layers, like your parameters, some are going through the roof. So this is like another very commonly used layer called batch normalization. And this is our LSTM layer.
Can you copy that line into the chat, please?
Yes. Where's the chat? Here. I think if we're using a same data sets, it should be like this. It could be X shape. I think this one is generally like the shape of X. Yeah, use this one instead. I think this one works. Yep, perfect. So this one need to declare the shape of the input. Chat. Yeah, normally I would use LSTM as a first layer. Otherwise, you need to do some like changing the model dimensions in the middle. So this is the LSTM layer. And then because afterwards, remember this one is like putting like 80 parameters in 80 baskets. And then in order to work for the dense layer, it needs to be like 80 parameters in one basket. That's why there is a flatten layer here, just to put the reduce the 80 baskets to just one basket that has like 80 parameters in there, just to flatten the numbers. You'll be probably familiar with the term if you use Grasshopper. So it's basically the same thing. You're flattening all the layers, all the numbers in the tree. So there's like flattening there. And then you can go on add your other like dense layers that you're using. So like you can add a few more, and maybe you can add some dropouts. So after this part, it's all the same as yesterday. Another thing is that in this case, LSTM only put in 16 units. Feel free to add some more, but just a reminder, this layer, the LSTM layer, has many more parameters than our typical neural net layer. In this way, if you're having more like units here, it will become extremely slow. So this one is a lot more slower than our typical dense layer. So be aware of that when you're tweaking the parameter here. And after that, in order for it to work, we need to add this one. Yeah.
Can you copy maybe all the paragraph in the model sequential, please? And could you, yeah, all that in the chat? Yeah, so we have exactly the same. Thank you very much.
No worry. Okay. You can remove the hashtag parts. I'm just. And there are a lot more like hidden parameters in here that you can also tweak with if you're using like a more complicated, using it for like more complicated tasks. Oops. My computer crashed. One moment. Wait, let me stop share. Sorry, computer crashed. Yeah. Can you guys see my computer? Hello?
I can see your browser screen. It looks like it's frozen at the moment.
Okay, so applications. One moment, I need to join again. Okay, so if you just search Keras in the LSTM, just search LSTM and the Keras, it has a lot of like hidden parameters like bias, initializer, bias, like regularizer. Like if you take Google any, let's say, YouTube course that talks about LSTM, most of them like the recurrent dropout, like dropouts, bias constraint, for example, like if it's go backwards, time major, or like unit forget bias. So if you can go to YouTube and get any introduction course on the LSTM, and it will give you some intuitive idea on what each parameter is, and you can start to play with them if necessary. But those are for like more complicated tasks, but not for our task. Our task is rather simple. You can just change the like amount of neurons in these layers and see what happens. So now you see it's like this one is very slow. It's like far slower than the previous ones. I think the batch size is a bit small as well, like 16. And in order for it to work, we also need to add this line. So it's before the model fit. So this one is actually the training process. We need to add this line. Just delete this one. Basically, we need to reshape the X, put each number in its own individual basket, and change it to this data structure. So basically, reshape X into this data structure. Let's edit this one only for LSTM. And then you can start training.
Can you could you please put that line the
Yep.
XX right, please? Thank you.
Yep. Don't worry. Yep. Just make sure everyone know where to copy. It's here, just before the model fit. You can just copy over there. Yep. Everyone got it? I assume. So, and move all the way down. So remember, we also need to use the same model to predict as well. So this after, so before we save things and calculate the score, we also add this line. So basically, whenever we try to use the model before that, we need to reshape X into a format that works for LSTM. So we also need to reshape X test. And copy this one in here. Yeah, it's also in the chat. And the last part that I need to add is here. One moment. This for LSTM. So this is the last part, like on the bottom, that we try to get one sample from our test and try to use for the apply the model on the test set to see how it works. But there is a reverse of order and accent text in the naming of the parameters, which shouldn't happen, but anyway. So those are the 3 lines we need to add in order for the model to work. Basically, just minor changing the data structure. So I'll give everyone like a moment to sort everything out and then let it to start training a little bit. I would recommend to change some parameter here so we're not like all training the same model. Just change it to whatever you want. It will take a while to train while we're talking about other things in the background. Feel free to change certain parameter here. So probably we want like slightly more units. While everyone is working on the training, I will give the following code. You can use this to replace the item optimizer. So this is like the called scoretic. I forgot the gradient descent. Basically, this is the gradient descent with with learning rate decay. So if you're running into problem of like more like zigzagging or up and down on the very tail, feel free to play with these parameters. So the first one, LR means learning rate, and the decay 1 to the -6 of x, is like the rate of decay, and the momento is just consider how much of a momento it tends to keep on the current path. But just feel free to play around with these numbers to see the outcome, if there's a change in the outcome. So this is like another gradient descent method. So originally we were using the Adam. Right now we're using like SGD. So here are a few more parameters for everyone to play with tonight. There's a kernel. I need to restart. So everyone has the code running. Are there any problem with anyone? I mean, you can still use the Adam optimizer if you want, because the SGD can a bit tricky to like to find the right parameters. Adam is pretty average. It works on mostly everything, at least in our case. So we need to import optimizer. To also add this one. In order for SGD to work, we also need to import optimizer. Oops. So you will notice it's a lot slower than the dense neural net version. So everyone has the code running. Raise your hand if or say something if you don't have it running.
I copied the last part that you sent, and
The
the optimizer is not defined.
so if you look at the Zoom chat, there is a sorry. From here, from Keras import optimizer. So replace that line with this one. So it's my fault. From Keras import optimizer.
Now it's running. Thank
Yep. Welcome. So let's just allow it to play in the background. And with let's open the notebook from yesterday. So we're going to spend some time on the image processing while waiting for our very slow LSTM to run. So it started with this movie to image. Has everyone copied the movie file and stored it into your folder? Like this movie file. It's not our lecture recording. This one on the Google Drive. Yep. I assume just everyone have it. So
Is there a particular location where we need to put the movie file?
Just next to your code. So those are the model, movie to image. So just next to the code.
Can you reshare it, please, the link?
Okay. I don't have it with me. Does anyone has a link? Can you post it into the chat? Anyone has a link? All silence. Wait, let me see. Google Drive. Come on, browser. So this one.
I found the link.
Okay, perfect. So this is a raw clip. Just give you guys a second. But so this is a raw clip. So this one is a lot more slower than the fast forward version. So we can assume, let's say each state is a static state for the synthetic rubber. And there are a few constraints. For example, like the gripper for the robotic arm, they are always like horizontally aligned. So this only moves along the x-axis. And obviously you can see there are a lot of like noise in the background, like different lighting and some like uncovered white areas in the background. So the first step is that we don't want this like white curtains to be disruptive to our outcome. So we need to crop out an area, for example, like here. I know we will have like different process for like a different experiment. And if you're using it, probably you are like using a different process method. But I just think going through this workflow give you right amount of anticipation of the workload or where to start. So the first part is like, so XE X1, X2, Y1, Y2 are the cropping areas, location on the pixel on where to crop. So this one is like, so the here. So use this method, the use of frame in this one to create to crop out. So there are a lot of nuances code that are based on the OpenCV library. If you don't understand, don't worry about it. And there are some customized program for you that were like, you can view them here. Let me see this one, image utilities. So those were all the program that we have developed for this, not program, like all the method and functions that we have developed to process the data. And if you're curious on how is it achieved, you can look in here. I'll give like a brief explanation on in theory how those works. And then this method is to extract every 200 frame from the video. So this one, if the count can be subdivided by like 200, then we extract one frame. So those are just numbers depending on with a lot testing and see which number works the magic. And then so this is like a very easy processing procedures. And this is like just some code that loops through all the videos in the folder. Currently, we only have one video in the folder, but in case we have more videos that we don't want to input them one-to-one, we can use this loop to find all the videos in a folder and generate image for everything. So this is like a one very small component. One moment, I'm picking up. Sorry, I'm picking up like important phone call. Hi, sorry, I'm back taking a phone call. So if you have successfully run these procedures, you should have like all this image sequence in the image test. So that's like the image processing from the video part. And if you're working with other video materials, you can use this one as well. So the second one is the image step. This one is a bit tricky. Actually, most people thought like the difficult part is the neural net parts, but in reality, the most difficult part are the image processing part. And the data preparation and the feature extraction in reality is like far more difficult than the training of neural net itself, unless you're like a scientist that studies neural net. So first of all, let's start with grabbing an image from the image folder and just get the latest frame. So this is the latest frame that we're going to use as an example. The second step is to turn it into grayscale. So this part, it's like pre-existing library in OpenCV2. You can convert colors. You can just reduce it to a grayscale. And the second part, sorry, one moment. Yep. So the second part is a slightly more difficult, is to get rid of all the noise. So this one at the infill, the whole use similar algorithm. So this is something that we have developed ourselves. So there are, for all the image processing, there are always part of the elements that it's more efficient if you just do it yourself, besides relying on other libraries. So okay, so I will just share my screen here to give you an outlook on how this one is achieved. So this is very interesting. So this is like one of those kind of smaller piece of software that you can just write yourself to achieve what you want. So for example, if there are some spikes here and there, what you can do is that, for example, like the background is all black, it will sort of scan line by line, and suddenly it says like here is a white pixel. It will start to reach around other regions and calculate all the white pixels in this region. And obviously, if it's like if it's one of the main body, there will be like a certain amount of white pixel in here. But if it's like a noise, like the white pixel in this region will be like only a limited numbers. For example, let's say smaller than 20 pixels, it's considered a noise, and we will just fill those 20 pixels in. So this one will search here. Okay, so this one is only like 12 pixels of a white region, then they will just fill in this 12 pixels of white region and so on. So this is like a small steps to get rid of the noise. I mean, there are a lot of like pre-existing libraries to get rid of the noise in the picture, but those are more for like movies and etc. It just doesn't work as you want it to. And the same thing is like to get rid of all the black dots in here. So it's like the same process, but just with the black color. So if it start to find like a black region, it start to count how big the black region is. If it's very small, like just 5-6 pixels, they will just remove this one and fill this one with white pixels. So this is like a very common method of finding noise in the picture and try to remove the noise. And the same method we would use for like tomorrow's timber image processing. So the timber is from like an industrial setting. So normally you would see like a timber scan like this, but because it's from industrial setting, it will sometimes, it's a bit exaggerating, but it sometimes will have like spikes like this that comes from like scanners, like the light leaking. So this one, like we also use similar method. It's like we scan here and see how wide this non-black pixel region is. So if this distance from both ends is very small, it means it have to be an arrow speck, because for our timber piece, it's very long. So there's like a significant contrast of the noise and the mean body. So if it's a noise, we will just like infill it with black and making a background to get rid of the noise. So it's like a very common method to get rid of the noise just by calculating the size and width of the region. And so it's the same thing. So this one is get rid of the white noise, and this one is just just fill in the white noise and remove the black dots in the interior. The step 6 is let me just play them, run them from the top. So make sure everything's running. Yeah, the removing of the black dots may take a bit longer. Okay. So then if we just really zoom in at the edge, let me see if we can just make it bigger. So you can see, because the image is captured at a low resolution, the edge is extremely zigzagging. Consider you're trying to find like a vector and the depths on this kind of like zigzagging profile. It's like a nightmare. So the next step is that we try to smooth this edge. And then there's like smoothing mechanism just to fill in the gap and get like this smoother edge. And with this method, we can get like the bottom curvature. And the way to get the bottom curvature is quite simple. Is that you start at a place near the end and go upwards, in the first white pixel you reach is on the bottom, of course. And then you try to get this like a neighboring pixels that are the border of white and black. So if like one side is white, one side is black, it's a border pixel. And trying to find the other way till where they start to turn 90 degrees. So without really turning a sharp angle, you're able to find like the bottom curve. And then we extract the middle curve. So remember what we mentioned, because like the top line, so you can see the top profile is very zigzagging even after smooth. And we often have this kind of arrows. So it's like some common arrows in image processing, image capture, like here. So I think this one could just be a problem with a water jet. So it has like a dent. So in order to avoid all those noise, we take like the midline. So the midline is a lot more smooth and average, and it's like a common way to extract midline in image processing. And there are a lot of existing library to find the middle line. So this one we use is to also in CV2, but to get the skeleton of the profile. So in the end, here is the middle line. Yeah. And if your capturing quality is really poor, it's possible just to have, so they got like one middle line and having a little bit of branching here. If like say the profile has certain spike or like abnormalities, it's sometimes for some of the image it will have like a small branch here and there. They are used to the optimized skeleton to just find like the longest branch and get rid of all the short branch, which is like also a common algorithm. So then there is extracting training data point. I think the text here is pretty self-explanatory. One moment, where we are, just run it again. So remove black from the interior. I think we have been here. Yep, I think so. My computer is just being slow. So this is extracting the middle line. And then we have the sample the bottom curve. So this is a bit a part that we need to a bit of measurement in real time. So according to our measurements, like 1 pixel length on the image equals to 1.92 centimeters. So that was like purely based on measurement to map the length in the picture to the length in the real time. So this process is just sample at the bottom curve, find the normal of the bottom curve, and find the intersect the normal with the mid curve. And I'll just grab sketch here. So this is quite straight. Like those are all very straightforward. It's like a grasshopper. It's just that you need to spend the time and patience to realize everything. So from the bottom curve, we start to sample. So it's not between the pixie, but the intervals of our sampling point. Like each interval is about 1.92 centimeters, and at each point. So this is the bottom line, and we already have like the midline, the middle skeleton, and then we have this one, the normal, and the go like the more normal of the point, and go upwards, and it will intersect with the midline at a certain point. I'll get another one, and so the distance between the bottom and the midline. So this point is like half height. And if you multiply this one by 2, you will get the full height. So this one will document the bottom point, the middle point. We will also document the normal. So the vector going here, we will also document the height in between. So and put those into the data sets that we're going to use for the training of the neural network. So for each of the feature point, there are 4 numbers collected, like bottom, middle point, and gradient. So if we have like the vector here, then we can transfer them to gradient here, gradient, and the height, material height. So those 4 data are collected at each feature point. And yeah, start to. And here is a visualization of all the like the heights that we have got from the model. So each height. And you can overlay this one with the original image and see how it looks like. I think this one, all of them are saved at somewhere. Image model deep step. Yep, here. So yep, it gives you some visualization of your outcome. Normally, it's just give you a visual reference to see if everything is working as you're expecting it to be. Is anyone speaking? Yeah. So this is like a give you a visual reference of what you have exported and the outcome of your image processing. Just give you some intuitive method to check if like all the data looks approximately right. You can run this or you don't need to run this. So this one is basically it's gonna run all the image in the data. So the process before is just based on one image. For this one is just going to batch run all the image in the folder and automatically save it to a data set. And then it is saved into this data set, np.save with all the data that are processed from all the images. So this is like a fairly straightforward image processing mechanism. There's no AI used in there, but just a normal image processing algorithm. So it works well in this case because in this case, we don't have time and effort to train a neural net to make this kind of recognition. It's just too time consuming. But this kind of labeling process can be easily achieved with like traditional image processing method. Okay, so wait, are we running over time? Okay, no, we're on time. Good. So are there any questions for the LSTM and the image processing? So we'll have the same flow that ideally each should generate 3 PDF of the LSTM system using the LSTM system in combination with the dense model to see what is the best quality, best model you can achieve. Let's check if we have things here. So in this case, this one is not that good. It's obviously because each of my like learning rate is too small. I think I started learning rate of 0.02, which is too small. But if you can change it to like 0.04, it's maybe could be better. Or you can just training it with more epoch. So the thing about the learning rate, because before we were using this kind of Adam optimizer, it's like a default learning rate. Now we're giving it our own learning rate. So for when we're assigning our own learning rate, a few things to take notice. Clear everything. Imagine your so should not be like this, but like this. About the steps of learning rate. So ideally, for example, if it's like something looks like this, the learning rate, so at each iterations, it will have a vector. So it knows it's like lower on this side. So for the learning rate, it depending on the step. The bigger step is that you can reach the bottom faster. For example, if you're having a very big learning rate, each step is like this long. So it takes 2 iterations or 2 epochs to reach this position. So the problem only come after you reach this position. If you start to take a stride of this long, let's say here, you will end up on this side, and like here, it will end up here, and sometimes the next step is like here. So basically, with a bigger learning rate, you will reach the bottom quickly, but then you will have a problem of, let's say here, you will have a problem of like oscillating a lot in the bottom. With a smaller learning rate, let's say a very small step, perhaps you will take you like 6 epoch to reach here, and you will have like smaller level of oscillation in here. And because we're using SDJ, it like has a learning rate decay. So be careful. I think in my experiment, I started with a very small learning rate. So it's just taking a while, taking like maybe 20 epochs to maybe just reach here. So it maybe just happened 20 iterations and the model only decreased to here. So either you, in this case, either you start with like bigger stride and with a lot of a higher proportion of decay on the bottom, or you can just keep the smaller step and having more training epoch on the bottom. So if, for example, currently I'm on the 20 epoch and maybe only here, if I train it for another 100 iterations, I may be able to get here. So it's a balance between time and the step and the iterations and the like training time and how many epoch you need. So let's have a little bit fun for tonight, and there will be like another tutorial session for tonight. If anyone has problem, any questions to ask. So good luck, or any last questions? Okay, so we will also each generate 3 PDF for the best, worst, and the average model for comparison. Yes. Was anyone speaking? No. Good. Yeah. See you tomorrow.
Thank you. Bye bye.
Thank you so
Bye-bye.
much.
Bye bye. Welcome.